Welcome to our deep dive into Stephen Hawking's A Brief History of Time.
Oh, yeah, this one.
It's a book that really captured the world's imagination. I mean, staying on the London Sunday Times bestseller list for 237 weeks,
Wow.
almost 5 years.
That's incredible.
Surely something else.
Yeah.
And today we're going to explore some of the amazing ideas in it.
You know, it's fascinating how Hawking was able to take these complex ideas from theoretical physics
Right.
and make them understandable
Yeah,
to a huge audience. I mean, he really had a knack for making science accessible.
absolutely. To really get a sense of how far we've come, let's go all the way back to the ancient Greeks
Okay.
and how they saw the universe.
All right, so back then, someone like Aristotle pictured the universe with Earth at the center.
Hmm.
Everything, the sun, moon, planets, stars, all revolving around us in perfect circles.
It seems so simple now, doesn't it?
It does.
But it's interesting how those ideas stuck around for centuries.
Yeah, they did.
Yeah.
In the 2nd century AD Ptolemy, he expanded on this model.
Yeah.
He incorporated more observations, and he created this really elaborate system to explain how everything moved in the sky, but still keeping Earth right in the middle.
And this model, even though it wasn't perfect,
Yeah.
it was really influential for over 1,000 years.
It really was.
Yeah.
But here's the funny part.
Okay.
Even Ptolemy, he knew there were some problems with his model.
Oh, really?
Yeah, for instance, it predicted that the moon should sometimes look twice as big,
Huh.
something he couldn't explain.
I'm curious. Why do you think, even after noticing that flaw, Ptolemy still held on to the Earth-centered idea?
Well, you have to remember back then, scientific thought was totally mixed up with philosophy and religion.
Right.
The idea that Earth was the center of everything, it just fit in with how they saw the world.
Hmm.
It took a big change in thinking to challenge that.
And that change came with Copernicus.
Exactly.
He was the one who dared to suggest that the sun, not the Earth, was at the center.
Right. Copernicus, in the 16th century, he came up with this radical idea of a heliocentric system. You can just imagine the uproar it caused.
It must have met with some serious pushback.
Oh, yeah.
I mean, to suddenly move Earth from its central position,
Yeah.
it would have shaken up their whole understanding of the universe.
Absolutely.
Right.
And then along came Galileo with his groundbreaking invention,
Okay.
the telescope.
Ah.
His observations of the heavens provided solid evidence to support Copernicus's theory.
So Galileo looked through his telescope
Yeah.
and saw evidence that went against this age-old Earth-centered model.
Yeah, he made some really groundbreaking discoveries.
Like what?
Well, for one, he saw that Jupiter had moons orbiting. This went directly against the idea that everything revolved around Earth.
Wow.
It was a turning point in how we understood the cosmos.
It's incredible how just looking through a telescope could have such huge implications.
Yeah.
It shows how powerful observation is
Yeah,
and questioning what you think you know.
absolutely. And Galileo wasn't the only one. Kepler later on refined Copernicus's model. He found out that planets actually move in ellipses, not perfect circles.
Oh, interesting.
This led to a more precise understanding of how planets move.
So from Aristotle's simple circles to Kepler's ellipses, our picture of the solar system was getting more and more complex
It was.
and more accurate. But I'm guessing it was still not quite complete.
Right, that's where Isaac Newton comes in.
Ah, yes. Yeah.
His work changed science completely.
Newton's laws of motion and gravity, right?
Those are still taught in schools today,
Exactly.
hundreds of years later.
Yeah.
In his book, Principia Mathematica, published in 1687, he laid out his laws of motion and universal gravitation. These laws explained why planets move the way they do,
Wow.
not just in our solar system, but everywhere in the universe.
So Newton finally gave us a way to understand the forces that
Yes.
are moving these celestial objects.
Exactly.
It must have felt like such a major step forward.
Newton's laws worked perfectly for centuries,
Right.
but then scientists started studying light and things got a little tricky.
Yeah, light's a tricky one.
It doesn't quite follow the same rules as other objects.
Right.
So where did that leave our understanding of the universe?
Right. Where did that leave us?
That's when things took a really mind-bending turn.
Okay.
In the 20th century with Albert Einstein and his theory of relativity.
Einstein and relativity?
Yeah, Newton thought time was absolute ticking away at the same rate for everyone everywhere. But Einstein challenged that fundamental idea.
Einstein's theory of relativity, it's one of the most famous scientific theories ever,
It is.
but it's also known for being really hard to grasp.
It is complex, but also incredibly beautiful. Einstein's theory of special relativity, which came out in 1905,
Okay.
showed that the speed of light is constant for everyone, no matter how they're moving themselves. This seemingly simple idea leads to the mind-blowing conclusion that time is relative,
Okay.
meaning it can pass at different speeds for different people.
But doesn't that go against what we experience every day?
It does seem counterintuitive,
Right.
but it's been proven in experiments over and over again. Think of it this way. Imagine you have two clocks perfectly synced.
Okay.
If you keep one here on Earth
Yeah.
and send the other on a super fast trip through space,
Okay.
when they come back together, the clock that traveled will show a slightly earlier time.
So time isn't this fixed universal thing we thought it was.
Right.
It's flexible.
It's
It warps and bends depending on speed and gravity.
Exactly. And that's just the beginning. Einstein's theory of general relativity, published in 1915, went even further.
Okay.
It redefined gravity itself. It's not simply a force,
Oh.
but a curve in space-time caused by mass and energy.
Okay, I'm trying to wrap my head around this
Yeah.
space-time curvature. How do we even picture that?
Imagine a bowling ball on a trampoline.
Okay.
The ball makes a dip, curving the trampoline surface.
Okay.
Similarly, massive objects warp the fabric of space-time. Planets orbiting the sun aren't really being pulled by a force. They're moving along the curves created by the sun's mass in space-time.
So if I rolled a marble across that trampoline, its path would bend because of the dip created by the bowling ball.
Exactly.
And that's how planets fall towards the sun.
Precisely. And just like a heavier bowling ball would make a deeper dip, a more massive object creates a greater curve in space-time.
Okay.
That's what we feel as gravity.
That's a really helpful way to think about it.
Yeah.
It makes this abstract idea of space-time curvature a little easier to understand.
Right.
How do we know this is actually true?
Well, general relativity has been confirmed by lots of observations.
Such as?
One famous example is the bending of starlight around the sun during a solar eclipse.
Oh, right.
Einstein predicted that the sun's mass would warp space-time around it,
Okay.
causing light from distant stars to bend slightly as it passes by. During a solar eclipse, astronomers could actually observe this bending,
Wow.
confirming Einstein's prediction.
That's amazing.
It is.
We're talking about light, which is supposed to travel in straight lines,
Yeah.
being bent by the curvature of space-time?
Right.
It seems like something out of science fiction.
It's one of the most profound and elegant ideas in all of science. But it gets even more mind-boggling when we start talking about the expanding universe.
The expanding universe. Now, that's something I'm really curious about.
Okay.
If I remember correctly, this all started with Edwin Hubble
Yes.
and his incredible observations.
Got it. In the 1920s, Hubble made a revolutionary discovery. Galaxies are moving away from us. And the farther away they are, the faster they're moving.
Wait, so the whole universe is expanding?
It is.
That's a pretty massive idea to grasp.
It is. To figure this out, Hubble used something called redshift.
Redshift.
Do you know how the sound of a siren changes pitch as it moves towards or away from you?
Yeah, like when an ambulance passes by, the siren's pitch drops as it moves away.
Exactly. Light from distant galaxies gets stretched as the universe expands,
Okay.
making it appear redder. This redshift is like a cosmic speedometer,
Okay.
telling us how fast a galaxy is moving away from us. The farther away the galaxy, the greater the redshift, and the faster it's moving away.
So redshift is like a fingerprint
Yes.
of the expanding universe.
Right.
But if everything's moving away from us,
Yeah.
wouldn't that mean we're at the center of the universe?
That's a common thought, but it's not quite right.
Okay.
The expanding universe doesn't have one single center like an explosion would.
So how does that work?
Think of it like blowing up a balloon with dots on it.
Okay.
As the balloon expands, every dot sees all the other dots moving away from it. It doesn't matter which dot you pick.
Right.
They all see the same thing. There's no center on the balloon surface.
Ah, that makes sense.
Yeah.
So in the expanding universe, everything is moving away from everything else.
Exactly.
And there's no special central point. That's a pretty wild concept.
It is. And this leads to another interesting question.
What's that?
If the universe is expanding, was it once much smaller and denser?
That's where the Big Bang Theory comes in.
You got it.
The idea that the universe had a beginning, a point where everything was packed together incredibly hot and dense.
Exactly. The Big Bang Theory describes how the universe changed from that incredibly hot, dense state to its current vastness.
And we actually have evidence to back this up.
We do.
Like,
In 1964, two physicists, Arno Penzias and Robert Wilson, they accidentally discovered a faint signal. of microwave radiation coming from every direction in the sky.
Wow.
This radiation, called the cosmic microwave background, is considered the afterglow of the Big Bang itself.
Hold on, they accidentally discovered the afterglow of the Big Bang.
They did.
That's amazing.
It was like finding a fossil from the universe's earliest moments. It further supported the Big Bang theory as the main explanation for the universe's origin.
Wow, so we've gone from Aristotle's Earth-centered universe
Yeah.
to Einstein's concept of space-time.
Right.
And now we're talking about the Big Bang and the expansion of the universe.
Right.
It's incredible how much our understanding has changed over time.
It really is.
Yeah.
And it doesn't stop there.
Yeah.
There are still so many fascinating and mysterious things out there in the universe to explore.
Like what?
Objects like black holes. Perhaps the most mysterious entities in the cosmos.
Black holes.
Yeah,
Those definitely capture the imagination.
they do.
They're areas of space-time where gravity is so strong that nothing, not even light, can escape, right?
That's right. To understand them, we need to dive into what happens to stars when they die.
Okay, so what happens when a star runs out of fuel? Do they just kind of fade away?
Not exactly. They can go out with a bang, or rather, a collapse.
A collapse.
Stars are in a constant battle against their own gravity.
Okay.
During their active life, the outward pressure from nuclear fusion in their core
Right.
is pushing against the inward pull of gravity.
Mm.
But when a star uses up its nuclear fuel, this balance is broken.
So what happens then? Does the star just shrink?
For smaller stars, yes, they shrink into what we call white dwarfs.
Okay.
But for stars much bigger than our sun, the gravitational collapse is catastrophic.
Wow.
Imagine the Earth squeezed into the size of a marble.
That's some serious density.
It is. And this extreme density creates a region of space-time where gravity becomes so strong that nothing,
Yeah.
not even light, can escape. That's what we call a black hole.
So it's like a cosmic vacuum cleaner
Yeah.
sucking up everything that gets too close.
Right.
But if light can't escape, how do we even know they're there?
That's a great question. We can't see black holes directly,
Right.
but we can detect their presence by how their gravity affects nearby objects. For example, if a black hole is part of a binary star system,
Oh, okay.
we can see the other star orbiting an invisible but incredibly massive companion. This gravitational dance is strong evidence that a black hole is there.
So we're detecting these invisible objects by their effects on their surroundings.
Yes.
It's like seeing the shadow of something that's inherently invisible.
You got it.
That's pretty clever.
We can also detect the radiation emitted by matter falling into a black hole.
Wow.
As matter spirals inward, it gets superheated, releasing X-rays and other radiation that we can observe from Earth.
So we're starting to get a picture of how we can study these mysterious objects.
Right.
But what about the inside of a black hole? What's at the center?
This is where things get truly mind-blowing.
Okay.
At the center of a black hole, there's something called a singularity.
A singularity.
It's a point of infinite density where the laws of physics as we know them break down. It's a place where space and time are infinitely warped, and the very idea of time ceases to exist.
Infinite density and time stopping.
Yeah,
That's intense.
it is.
But if a singularity is a point of infinite density,
Yeah.
shouldn't its gravity be infinitely strong, pulling everything in the universe into it?
That's where the event horizon comes in.
Okay. The event horizon.
It's the boundary around a black hole beyond which there's no escape. Anything that crosses the event horizon is trapped forever inside the black hole's pull.
So the event horizon acts like a shield, protecting the rest of the universe from the singularity's infinite gravity.
Precisely. And while we can't directly see what's happening inside a black hole, Stephen Hawking made some groundbreaking discoveries about them.
Really?
He combined the theories of general relativity and quantum mechanics,
Okay.
and he realized that black holes aren't completely black after all.
Oh.
They actually emit a faint radiation,
Huh.
now known as Hawking radiation.
Wait, so black holes can actually lose mass.
They can.
But how's that possible if nothing can escape their gravity?
It's a complex process involving quantum fluctuations near the event horizon.
Okay.
Without getting too deep into the physics, imagine pairs of virtual particles constantly popping in and out of existence all over space.
Virtual particles?
These are particles that exist for a super short time.
Right.
Sometimes near the event horizon, one particle falls into the black hole
Okay.
while the other escapes.
Hmm.
This escaping particle carries away some of the black hole's energy, reducing its mass over time.
That's mind-blowing.
It is.
So even black holes, these seemingly eternal cosmic monsters,
Yeah.
they're not invincible.
Right.
They slowly evaporate over time, radiating their energy back into the universe. It's like a slow cosmic leak.
That's a great way to put it. This discovery was revolutionary because it connected general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which deals with the subatomic world.
So we've talked about gravity, relativity, the expanding universe, and black holes. What other incredible ideas does Stephen Hawking explore in A Brief History of Time?
One of the most fundamental concepts is quantum mechanics, which governs how particles behave at the atomic and subatomic levels.
Okay.
It's a world where things aren't as straightforward as they seem in our everyday experience.
What do you mean by things not being straightforward?
Well, in the quantum realm, particles don't act like tiny billiard balls. They exhibit something called wave-particle duality, meaning they can behave as both particles and waves.
So these tiny particles can be both a wave and a particle at the same time?
You could say that it's one of the big mysteries of quantum mechanics.
Wow.
And it gets even stranger.
Yeah.
One of the most famous principles in quantum mechanics is Heisenberg's uncertainty principle.
Heisenberg's uncertainty principle.
Yeah.
That's the one that says we can't know both the position and the momentum of a particle perfectly.
Exactly. It's not that our instruments aren't good enough. It's a fundamental property of nature itself.
Interesting.
The more precisely we know a particle's position,
Yeah.
the less we can know about its momentum, and vice versa.
So there's a limit to what we can know about the subatomic world.
Right.
There's always going to be some uncertainty.
Precisely. This inherent uncertainty has profound implications.
Such as?
It means predictions in quantum mechanics are always about probabilities, never certainties.
Okay.
We can only talk about the likelihood of finding a particle in a certain state, not its exact location or momentum. It's like the universe is playing dice with reality.
It really challenges our classic understanding of how the world works.
Instead-
Instead of fixed laws governing the universe,
Yeah.
we have probabilities and uncertainties. It's a completely new way of looking at reality.
It is, and it's one of the most fascinating and challenging parts of quantum mechanics. It forces us to reconsider what we thought we knew about cause and effect and determinism.
This deep dive is really living up to its name.
It is.
We've covered some heavy topics today,
We have.
from ancient Greek ideas about the universe to the mind-bending world of quantum mechanics.
Yeah.
And I have a feeling it's only going to get more mind-bending from here.
You're absolutely right.
Ah, buckle up.
Let's do it. We've talked about the beginning of the universe, but what about its end? And maybe even more fundamental, why does time seem to only go in one direction? That's the whole mystery of the arrow of time.
Yeah, it's like you don't really think about it until someone brings it up. We experience time moving forward, past to present to future, but is there a deeper reason for this directionality?
One possible explanation is the second law of thermodynamics. It says that the entropy or disorder of a closed system always goes up over time.
Okay.
Imagine a deck of cards all perfectly ordered.
Right.
Shuffle them, and they get disordered,
Right.
right?
Yeah.
It's not likely you'll shuffle them back into perfect order.
Right.
That's entropy at work.
So the universe is always becoming more disordered, like a room that never gets cleaned.
It's not exactly about messiness in the real world, but more about the number of ways things can be arranged. A really ordered state, like that perfectly ordered deck of cards,
Yeah.
has fewer possible arrangements than a disordered one. As time goes on, things tend to move towards states with more possible arrangements, so entropy increases.
So the universe is constantly shuffling itself into more and more disordered states.
Right.
And that gives time a direction always moving toward greater entropy.
Exactly. And the expansion of the universe itself provides another arrow of time.
Okay.
As the universe expands, it cools down. And this cooling can't be reversed. We can't go back to a hotter, denser universe.
So the expansion of the universe is like a one-way street for time, always heading toward a cooler, more expanded state.
Exactly. Like a cosmic wind-down clock.
Are there other arrows of time?
There's also the psychological arrow of time. It's about our perception and memory.
Okay.
It's why we remember the past,
Right.
but can't remember the future.
It's true, our memories work in one direction, but why can't we remember the future? Is that just our brains being limited?
That's a question that still puzzles philosophers and neuroscientists.
Yeah.
It's probably connected to how our brains handle information. The act of experiencing and remembering events creates a timeline
Right.
that defines how we see time flowing.
It's fascinating how these different eras of time, from thermodynamics to cosmology to our own perception, all seem to point the same way.
It is, and it leads to some truly mind-bending possibilities when we start thinking about things like wormholes and time travel.
Wormholes and time travel. Now we're getting into the really out there stuff.
Yeah.
Is there any science behind these ideas, or are they pure science fiction?
Well, we haven't directly seen wormholes or time travel.
Right.
They do show up as possibilities within the framework of general relativity.
Okay.
Wormholes are like theoretical tunnels or shortcuts through space-time. Imagine folding a piece of paper in half and poking a hole through it.
Right.
That hole connects two distant points on the paper.
Right.
A wormhole would be like that, connecting two different areas of space-time.
So we could theoretically travel vast distances across the universe, or even through time, using these wormholes, like taking a shortcut through the cosmos.
That's the idea.
Yeah.
But there are huge challenges and paradoxes that come with time travel.
Like, what kind of paradoxes? I'm picturing all those time travel movies where things go wrong.
One classic example is the grandfather paradox.
Okay.
What if you traveled back in time and stopped your grandparents from meeting? Would you then cease to exist?
That's a tough one.
It creates a logical contradiction.
Right. If I never existed, how could I have traveled back in time? It's a loop.
Exactly. Are there ways physicists deal with these paradoxes?
Are there?
One approach is the idea of consistent histories.
Consistent histories.
It suggests that even if time travel was possible, everything that happens in space-time has to make a consistent story.
Okay.
It can't break the laws of physics.
So you couldn't go back and change something that would create a logical impossibility.
Exactly. Time travel, if it's even real, would have to follow strict rules to stay consistent.
It's like the universe has safeguards
Right.
to stop time paradoxes from messing everything up.
But even though wormholes and time travel are still theoretical, is there any reason to think they could actually be possible?
Good question.
While we haven't observed them,
Right.
some solutions to Einstein's equations of general relativity do allow for them. The math doesn't rule them out.
Interesting.
However, creating and stabilizing a wormhole would need something we haven't found yet.
What's that?
Exotic matter with negative energy density.
Negative energy density. That sounds like something out of Star Trek.
It does. So we need some kind of hypothetical exotic matter to make wormholes and time travel work.
It's a big if.
It is. But even if we never achieve time travel or build a wormhole, just the possibility pushes the limits of our imagination
Yeah.
and makes us rethink what space and time really are.
It's amazing how these concepts change how we understand reality. But beyond wormholes and time travel, there's one big idea in physics that seems to connect everything: the search for a unified theory.
You're talking about the holy grail of physics. A single theory that could explain all four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force.
It's like finding the master key that unlocks all the secrets of the universe. Are we getting close?
One of the most promising candidates is string theory.
String theory.
It's a radical idea that says the basic building blocks of the universe aren't point-like particles,
Right.
but tiny vibrating strings.
Strings. So everything in the universe, from galaxies to atoms to light itself, is made up of these tiny vibrating strings.
Exactly. And just like a violin string can make different notes depending on how it vibrates,
Right.
different vibrations of these fundamental strings create different particles and forces.
It's a pretty elegant idea. But how does string theory explain the four fundamental forces? How does it all fit together?
Each force is connected to a specific type of string vibration.
Okay.
Gravity, for example, is thought to be carried by closed loops of string, while other forces are linked to open strings. By describing all forces and particles in terms of string vibrations, string theory tries to unify all of physics under one framework.
Like finding a universal language to describe everything in the universe.
Exactly.
The big goal. What about those extra dimensions that string theory needs? How can we make sense of that with our experience of a three-dimensional world?
That's one of the trickiest parts of string theory. It proposes more than just the usual 3 spatial dimensions and 1 time dimension.
Yeah.
Some versions need 10 or even 11 dimensions.
10 or 11 dimensions, that's beyond what I can even imagine. Where are these extra dimensions? Why don't we experience them?
The idea is that these extra dimensions are curled up or compactified into tiny spaces, much smaller than we can see right now.
So they're hidden from our perception, woven into space-time, but too small for us to detect.
That's one way to think about it. It's
Yeah.
a mind-boggling concept,
Yeah.
but it's at the forefront of our attempts to understand the fundamental nature of reality.
String theory and this search for a unified theory really push the limits of what we thought we knew about the universe. It's amazing to think we might one day have a single theory that explains everything from the tiniest particles to the biggest cosmic structures.
It would be a remarkable achievement.
Yeah.
And while we might not have all the answers yet, the pursuit of a unified theory drives science and pushes us to ask even deeper questions about the nature of reality.
Yeah. I'm curious, with all the complexities of the universe we've talked about, what's one thing you'd like our listener to think about as they keep exploring these ideas in A Brief History of Time?
Well, we've talked about the Big Bang and the universe expanding, but what got it all started? What was there before the beginning? Hawking explores something called the no-boundary proposal. It suggests that the universe way back in its earliest moments didn't have a defined beginning or boundary. It's a really tough concept to wrap your head around.
Yeah.
It challenges our linear understanding of time.
It does. The no-boundary proposal suggests that asking what came before the Big Bang is kind of like asking what's south of the South Pole, a question that might not even make sense with how we currently understand the universe.
Exactly. And when we combine this with what we know about quantum mechanics, it brings up another fascinating question.
Mhm.
If the universe started with very little non-uniformity, as quantum mechanics suggests, could our existence be traced back to a tiny quantum fluctuation in those very early moments?
It's a pretty profound thought. Our whole universe, everything we know and experience, could be the result of a random quantum event in the distant past. It makes you realize how connected everything is, from the smallest subatomic particle to the largest cosmic structure.
Absolutely. And it shows how much we still don't know. There are so many mysteries left to uncover, so many questions still unanswered. A Brief History of Time is a great place to start for anyone who wants to explore these mysteries.
It's definitely been an inspiring journey for me. We've covered so much today, from how the ancient Greeks saw the cosmos to the mind-bending possibilities of string theory and the very essence of time itself. I feel like we've just scratched the surface.
It's a book that you can read multiple times. Each
Mhm.
time you go back to it, you're likely to find new insights and make new connections.
And that's the beauty of science, isn't it? There's always more to learn, more to discover. It's an endless quest for understanding.
It is.
Yeah.
And that quest for understanding, that drive to figure out the mysteries of the universe, is what makes science so captivating.
Well, I want to thank you for joining me on this incredible deep dive into A Brief History of Time. It's been a true pleasure exploring these mind-blowing ideas with you.
The pleasure was mine.
And to our listeners, we hope you've enjoyed this journey as well. We encourage you to grab a copy of A Brief History of Time and continue exploring the wonders of the universe for yourselves. Who knows what amazing discoveries are waiting for us in the future? Until next time, keep looking up at the stars and never stop asking those big questions.